So thanks for staying late. Um, my name is Itamar Colvin, and I'm going to talk about the topology of cracks. And so I guess everybody knows the joke that a topologist can't tell a coffee cup from a donut. And I would like to ask if a topologist can tell the difference between a crack, like you see here in the cliff, and a bagel, like maybe you've seen today in the old city. And this work was done together with Gil Cohen and Mokhtar Adobedia, which sits here, and of course with Jay, who's why we're here. So I'll start by saying something about topology. So topology is a set of properties that doesn't change under smooth deformations. So they doesn't change if we, for example, stretch or bend or twist a surface. But we do change the topology if we make a tear or glue two bodies together. And the main problem in topology is to determine what properties are invariant under smooth deformations. So one thing that doesn't change under smooth deformations are the local neighborhoods of points. So we can think about four generic types of neighborhoods. One is regular points, where the neighborhood is a plane. You can think of a boundary point where the neighborhood is a half of plane, like in this spherical cup. And there can also be double points where two planes are tangent or intersect, and or triple points where three planes intersect. And a simple illustration of a triple point is by taking a piece of paper, making a fold halfway through, and now you see that you have a line of points where you have two tangent planes and a single point where you have three tangent planes, which is a triple point. So this is not topologically equivalent to a flat piece of paper. And the question of my talk is, what is the topology of a crack? So if we take a three-dimensional crack like you see here, then a fracture occurs along a line called the crack front. And if we abstract from it only the crack faces, then we see that the crack front is actually a double line. It's the intersection of the two crack surfaces. And inspired by topology, we can ask what happens if we smoothly deform the crack front. Or perturb it? Does perturbation grow with crack propagation? And theoretical works from the last 30 years tell us that perturbations should decay, and this includes in-plane perturbations or perturbations in the plane of the crack, or out-of-plane perturbations perpendicular to the crack. So this means that without changing the topology, we should see only flat fracture surfaces. But of course, if you go to experiment, you should see Will Steiner's poster. So if you go to experiments, you see a lot of structure. So one type of surface structure, which is very common in slow fracture, or where when the cracks are much slower than the Rayleigh wave speed, is these stepped surfaces. So you see them in disparate materials, such as silicon and rubber and gels. And so again, I recommend seeing Will Steiner's poster, which deals with these features. And another type of structure which you heard about earlier today are microbranches that appear in fast fracture. So microbranches are structures that are localized across the fracture surface, and they consist of cracks or microcracks that penetrate into the material. How does the crack form surface structure, right? So you might guess that it need to change the topology, but to understand that, we perform experiments where we directly visualize the dynamics of the crack front in brittle gels. The reason we use gels is because the gels are soft, crack wave speeds are slow, and also crack speeds. So we are able to visualize them in real time. In an experiment, we take a gel sample we insert a seed crack, and we shine light through the sample. And what happens is that if the material is intact, the light just passes through. And if the material is broken, light gets scattered away. And what we get is a shadow image where the crack front is the boundary or between the shadow and the illuminated frame. And okay, so here's here's a typical movie showing a propagation of a crack front while forming facets. And you can see that there are very delicate, slight perturbation to the crack front as it propagates, and each of these small perturbations correspond to one of these steps.
What's the time scale?
Sorry. So the time scale here must be. Okay, I can tell you the velocity of the crack, which is here it's about 4 centimeters per second. So I'm thinking the whole thing must be something like a few microseconds, milliseconds. Sorry. So if we focus on a single step, like you see here, and yeah, wait for it to stop. Okay, and we extract the crack front shape. We see, we zoom in. We see that we have quite a long range of front deformation, and this deformation contrasts with the actual height of the step. So this is a profilometric measurement of the fracture surface, which we make after the experiment. And we see that if we take a cross-section along the step, that the step is highly localized on the order of 30 to 50 microns. So what is the origin of this deformation? If we go back to fracture mechanics, which we heard about it a few times today, then we know that to propagate a crack, we need to pay some energetic cost to break bonds. And the energy to break the bonds comes from the elastic energy in the material. And this elastic energy flux must equal the dissipation in creating the new surface. Now, when you have a deformation in your crack front, as Jim Rice have shown in 85, your elastic energy flux or energy release rate becomes modulated along the crack front. And when you have curvature, this means that you also get an increased energy flux. On the other hand, when you have, for example, a step or some surface structure, then this means that the dissipation here is higher because you create more surface. So energy balance tells us that both of these changes must balance each other, and therefore we can use the crack front profile to estimate how much energy was dissipated locally, and in particular how much area was created. And I use this capital H to denote the total added area per unit crack length. So does this picture apply for our case? We take a crack fronts and compute the predicted added area, and we can also directly measure the step height. And here we see that for a range of steady state steps that we get more or less the same value. We complement these measurements by an event of nucleation of two steps, where each point here is taken from a single crack front, and also an event of a merger of two steps. So two steps can merge, resulting in a big step, which then decays into the steady height. And overall, we see a proportionality between these two, between the predicted added area and the step height. Now, okay, so energy balance works, luckily. And this observation raises the question, why does the total added area per unit crack length is bigger than the step height? And the reason that's puzzling is because if you take a simple step of height h and width w, then the total added area that you expect to have must always be smaller than the step height. This is by simple geometry. And the way out of this puzzle is to take a closer look at the fracture surface, take a cross section across one of these steps, and then what you see is that beneath the step, one of the sides of the fracture surface extends beneath the step, and this means that your added area is actually increased by 100%. So the way to explain this hidden surface formation is by changing topology of the crack front, as you might have guessed. And in this new topology, the crack front is separated into two branches which lag one behind another. And the lagging branch is connected to one of the faces of the advanced branch in a triple point, as you can see here. Another thing that topology gives us is that it causes the step persistence. So as shown previously in works in 2D fracture, when a crack branches, the two branches repel each other because the piece of material between them cannot hold stress. And on the other hand, we have long-range stresses that attempt to suppress deviations along the crack front. So topology increases dissipation and also leads to step persistence. Now, so now I would like to tell you something about microbranching. So we see microbranching when we increase our velocity. So at around 0.05, we start seeing microbranching coexisting with the facets, and at 0.1 of the Rayleigh wave speed, we see just branch lines. And here's a movie showing how the in-plane Franck dynamics, when one microbranch is formed, you see it generates curvature and collapses into a cusp, forming this localized microbranch. And the funny thing is that in the same regime, we also see divergence of steps during facet formation. So comparing these two, we gave us the thought that maybe what we see is a transition from a divergence of steps or step lines to a convergence of step lines, and we wanted to understand how can this happen. So we came up with a simplified model for crack front dynamics. You can see more details in poster 8. In this simplified model, we assume that the crack front is confined to a plane. We take into account the effect of surface structure only as a local increase in dissipation along the fracture plane. And we solve and we find the equation of motion for the crack front in the context of a scalar elasticity, which is a sort of a reduced model when you only have one bulk mode instead of three. So again, going back to energy balance, we can derive an expression linking the local velocity along the crack front to the history and dissipation. And okay, so these are the parameters the dynamics depend upon, but the main idea is that you can use energy balance to derive an equation of motion for the crack front. And if we add steps or local distribution of dissipation to the model, and assume that that steps drift along the crack front and grow as you can see from the height measurements taking along the backbone of a step here, then we can we model this process with a distribution that drifts that is centered around z naught and has a width w which grows over time. And we also assign an amplitude to this surface area distribution. So it's not that there's actually surface area created, but we model how much dissipation would happen if there was a surface structure there. So here's a result of a solution. Here's a solution of the equation of motion for d equals 2. And if we increase the amplitude of dissipation, we can see that instead of diverging, these two dissipation distributions actually converge. And in the experiment, what we think happens is that it's not that the amplitude of dissipation changes, but that inside the microbranch you have a lot of inner structure that increases the dissipation. So I mean, this is still a sort of a qualitative explanation, but we think it has the right components. So for the last slide, I'd like to tell you a little bit what we think happens in 3D when two steps converge during microbranching. So here you see a crack before a microbranching event from the top. Here you see the crack front in a similar event, and this is the 3D picture. So at first you have a nucleation of two steps, and you have some curvature along the crack front, and it's maybe a little bit hard to see, but there is a formation of a caustic at the tip of the crack, or some blunting of the tip of the crack. This blunting grows as well as the curvature, and we understand it as the convergence of these two steps, which finally intersect, forming a ligament that you see here. And this ligament ruptures, leaving a small bump on the surface. And in the end, the resulting fracture surfaces look like that. So these are the two fracture surfaces from the same event. And I think what's interesting is usually when you talk about brittle materials, you say that the two complementary surfaces should look exactly like the negative of each other. But here you see that this complex topology leads to a dissimilarity between the surfaces. So I hope I convinced you that topology is important for fracture, and I thank you for your attention.
First of all, wow, the last slide. Going back, do you have any idea where the 50 micron step size?
Why?
Where do we get a scale?
I have an idea, but
Private, like
it's denominator.
So some process or microscopic scale. Could you change? Test it?
I can comment on it,
Okay.
but
You're allowed.
yeah. So I think step growth is a bit a difficult. It's a bit of an involved process, but when we look at double nucleations like you see here, it seems that they grow without a scale, except this like nucleation scale, and then at some point they saturate, or not saturate, by change the exponent, and we see that it happens when it comes at some distance from either the boundaries of the sample or other steps. So nonlinear elasticity might play a role here, but we think that there should be other factors.
So perturbations decay theoretically if the mode 1 loading is perfect, but if there's any mode 3 admixture, then the situation's always unstable. Do you think it's possible that there's just a little bit that's always creeping in?
Well, I think, well, if we had a substantial mode 3 component in our experiments, we would see a preferential polarity of the steps. So you would see more steps in one direction than in another, and we see no such like asymmetry.
Locally, we create a mode 3.
Yeah, locally, of course, around the step, all modes should play their part.
Thanks. So with the transitional region where you have the mixed steps and microbranches, how sharp do you think the transition is?
Well, for the specific system I investigated, we see a transition between 0.05 and 0.1 of the Rayleigh wave speed, but I really don't know much more.
But so locally, you can slow down the crack significantly when you have a microbranch there, right? So that could lead to an adjacent area where you get a step.
And
locally it's
yeah, and actually you do see that. So
I mean, do you see have you looked for correlations, for example, in steps with adjacency of large areas where you have microbranches?
So I think usually what happens, but again, I'm saying only from what I've seen and not. So you can have many microbranches or branch lines which decelerate your crack, and then you go over to a faceting regime, and I mean the two regime can be intermittent in the same sample. So yeah, I don't. It's not a very well defined transition.
Okay, I believe it's all for today. So let's thank Itamar again.